Okay, on this parent function's foldable, we're going to identify the parent function, and then we're going to work a couple of examples on various types of functions. So first of all is the linear function. So in order for us to graph something that we may not know the answer to, we're simply going to identify some values that we would choose for x, and then we'll identify what the y values should be. So the parent function for a linear function is y equals x, or we could rewrite it as f of x equals x. So we're going to choose some basic points, -2, or basic values of x, -2, -1, 0, 1, and 2. And when we substitute those values into this equation, we get y equals -2, y equals -1, y equals 0, y equals 1, and y equals 2. And so now we can take that information and plot those points over here. So -2, -2, -1, -1, 0, 0, 1, 1, 2, 2. And we see we have this nice straight line through the origin. And the origin is a key piece of information when we're dealing with parent functions. So here we have a graph y equals 1/3 x minus 2. Now we've already learned how to graph a slope-intercept form, so I'm just going to graph that the way we would do a graph slope-intercept. So we take this y-intercept, which is -2, and we plot a point there. And then the slope is, it's actually just -1/3, and so we're going to rise 1 and run 3, and we have a point there. We could also do it in the negative, rise -1, run -3, and we put a point there. And now we just have this nice straight line through here. Remember to put your arrowheads to be a line and not a line segment. And so there's our line, or our graph, excuse me, of this equation. And so this equation here. So now we can look at it and we can figure out that the domain for this is all reals, and the range is also all reals, because the arrows face in both directions, left and right, as well as up and down. Okay, here in example 2 we have the same kind of thing. We have a slope-intercept form, so we're going to take the intercept, which is +5. So on the y-axis we're going to go to +5 and put a point. Our slope is -2, so from here we're going to go down to +1, down to +1, and there's our line forming, and so we'll just draw a line through those points, put arrows on it, and again you'll see because the arrows are there, it's saying that it's going to the left and to the right forever and up and down forever. So our domain is all reals and our range is all reals. And you'll find for all linear functions that will be true. The domain and range will always be all reals. Okay, so for the absolute value function, again we're just going to select some values. So I'm going to select -2, -1, 0, 1, and 2. And when we substitute those values into our x, we'll come out with our y values. And so the absolute value of -2 is 2, the absolute value of -1 is 1, the absolute value of 0 is 0, the absolute value of 1 is 1, the absolute value of 2 is 2. And so now we can graph those. So we're going to go -2, 2, and there's a point, -1, 1, 0, 0, 1, 1, and 1, 2. And you'll see that we have this nice V with arrows saying that it's going on forever in the positive infinity direction. In this example, we should recognize from our translations that the output is being decreased by 3. So that means we're going to take our parent function and move it down by 3. So our vertex is down here at y equals -3, but nothing's changed with our x. So we can still graph our absolute value function the same as we had on the parent function. The only thing that changed is the location of the vertex. It slid down by 3. Okay, so now again our arrows point in both the negative and positive direction along the x-axis, so our domain is going to be all reals, but our y vertex, or our range, is limited to -3. We don't have any other values below -3, so our limitation is -3, and it goes all the way to positive infinity. -3 is included, so we put a box around it. In this example, we notice that our input has been added by 2. We also should note that it's been multiplied by a -1. So we're going to take our parent function and slide it to the left by 2. So our vertex is going to be here. The y didn't change, so the coordinates for y are still going to be 0. But now we also, because of the negative, that means that our graph has turned upside down. So that's going to be the graph of this one. So now that we know what the graph looks like, we can figure out the domain. So in this case, the domain is all reals, because the arrows go off in both the positive and negative direction, but our range has been limited to our vertex, and so the range goes from -infinity to 0, and 0 is included. So for our exponential functions, you'll notice that the x value is actually the exponent, hence exponential function. And so when we do these, we're actually going to use our -2 for x, -1, 0, 1, and 2. And in order to do the parent function, we actually have to define the parent function as being y equals 2 to the x. So when we take 2 and raise it to the -2 power, we actually get y equals 1/4. When we take 2 and raise it to the -1, we get y equals 1/2. 2 raised to the 0, anything raised to the 0, is 1. 2 raised to the first power is 2, and 2 raised to the second power is 4. Okay, so now we're going to just plot those. So we have -2 and 1/4, which is probably right around here. We have -1 and 1/2, which is about right there. 0 and 1, and 1 and 2, and then 2 and 4. And you'll see that exponential functions have this curve where it starts off slowly, but then it grows very rapidly. Okay, so here's example 5 of an exponential. So we're going to remember we're using these exponents as the, well, x, the value of x is the exponent. So we're going to take 4 to the -2, which gives us 1/16. And we're going to take 4 to the -1, which gives us 1/4. 4 to the 0 gives us 1, because anything raised to the 0 power is 1. 4 to the first power is just 4, and 4 to the second power is 16. So when we graph those, we get the following. So there are our points, and we can draw the curve. And again, it's growing very rapidly. Okay, so our domain in this case, you can't really tell very well what the domain might be, because you can't tell that this arrow continues to move a little bit more and more to the right, but it definitely is going to the left. So our domain on this is really all reals. But our range has been limited. So if you think about it, there's no way to ever get 4 raised to a power to equal 0. So it's going to get really, really close to 0, but it'll never get there. So our range is y is greater than 0. And a lot of people will say greater than or equal to 0, because when you get so incredibly close to where you have 0.00000000001, they would say that's just 0. So we will say that y can equal 0, but it will never get below 0. Okay, and then for example 6 for exponentials, we're going to take negative 2 and raise it to the x power. So negative 2 raised to the negative 2 power is going to give us a negative 1/4. Negative 2 raised to the negative 1 is going to give us negative 1/2. Negative 2 raised to the 0 power is just going to be a negative 1. Now recognize that this negative is negating whatever is happening to the 2 raised to the exponent, so you have to keep that in mind. Negative 2 to the 1 power is going to be a negative 2, and negative 2 raised to the second power is going to give you a negative 4. And when we graph them, we get the following. So here are points, and we can draw the line to connect those. Now recognize that we have flipped this parent function upside down, and so when we do that, we're going to get a slightly different domain and range. Well, slightly different range anyway. Our domain is still going to be all reals, okay, because we're still going in the direction to negative infinity as well as the direction to positive infinity, because this still does have a bit of a slant to it. Okay, but as far as our range, notice that our range goes on in the direction of negative infinity, so we have negative infinity to 0. Or we can say y is less than or equal to 0.